All right. Good morning, everybody. Um, First, a couple of little housekeeping things to get us finished up for last quarter. Um, you guys should have just finished your bell ringer, and if you haven't done that yet, pause me. And you should also have your lab reports back. Again, if you don't have those, pause me. I wanted to talk a little bit about why we're doing the bell ringer, and then a little bit about your lab report and how that was graded and all that. So one of the things that kind of showed up to me on our last test is that we've got some folks, not everybody obviously, but not an insignificant amount either, uh, who don't really quite get the fundamentals of the problem working. And so what I want to do is I want to give you guys regular practice doing the basic stuff like mole conversions or molar mass calculations, or getting the empirical and molecular formula, because that's kind of stuff we'll use again and again, and you just aren't going to have too much of a opportunity to do those specifically, maybe once or twice a chapter. And to mitigate that, I'm going to get us to do these little bell ringers. It's 5 minutes a class that I think you guys can spare, or maybe 10 minutes a class that I think you guys can spare. And it's really going to do a world of good keeping you fresh on some of that stuff, because then it won't be 9 weeks since you've seen something. It will have only been 1 week because you did it, the week before in your bell ringer. Okay, so we're going to try and do those every class. I'm not saying we are going to do them every class. That will be it will not be a free grade, but I'm not going to say it's going to be a super strict grade that you have to get everything right on. And Miss Barron's going to show you how to work it every time afterwards. But those are going to come home to me, and I'm going to look at them. And so as long as it looks like we're putting forth effort and you guys are engaged, it's probably going to be a 5 out of 5. And so a nice little way to maybe give your grade some bump. But if it looks like you guys aren't putting forth the effort for it, I'll be glad to kind of zoom in on it and make sure that I'm counting off for not putting in effort, because that's what the daily grades are for. They're for engagement. They're for keeping you guys active. So let's try not to make it come to that. Let's just take the 5 points every day. When you come in, be ready to work, be ready to do the bell ringer. It's called a bell ringer. It's from my public school days at Forest Hill. It's basically supposed to be up when the bell rings, and then you guys are doing it. So anyway, that's that, and I hope you guys will benefit from that, both in your learning and in just your grade, getting a little bit of daily help in addition to homeworks. Okay, so your lab report, that was out of 66 points. Just to be frank about it, I didn't do a super great job on the rubric. I've never written a rubric for lab reports before. And for that reason, and the fact that this is probably most of y'all's very first time writing any kind of lab report, I was pretty lenient on the grading. I tried to not really criticize too heavily on a lot of stuff. I want us to improve every time, and I didn't think the best way to do that was to go ahead and just drop the hammer on this is not excellent scientific writing, because that's an unfair expectation that you guys would be excellent scientific writers. So just know that you can see on my little thing here, I've got some notes. I'm going to clarify the need for discussion of error specifically, as well as error calculations. And I even had an awesome typo there. Same typo I found in some of y'all's lab reports. but I got to make a couple of changes, and I'm going to do that for you guys so that we're all again on the same page for the next lab report. And there was a lot of, again, to be just frank, I spent a lot of time trying to give you guys good feedback on your lab reports so that you could take that, and the next time you write a lab report, you're, I was going to say interpolating. That's the wrong word, though. Using, the word will come to me. You're using all of those criticisms, those constructive criticisms there to do a better job next time, as well as hopefully the rubric will be a little bit more helpful for you at that point too. It was clear to me that you guys had not done a lot of scientific writing, which is cool. This is the time for you to be learning how to do that. But I really am going to expect you guys to put in the time, and I think that you'll see that whether you are a liberal arts kind of person in college and you just take biology 101, I mean, you still got to write lab reports even for that, no matter pretty much wherever you go to college. And I think it's going to make all of that a lot easier. It's going to make physics a lot easier next year as well, because guess what? Lab reports there too, okay? And what those are trying to do is to get you guys to think clearly about what we can and cannot draw conclusion-wise from data. It shows up in your lab reports, when y'all will say these results were conclusive and accurate and precise, and there's no way that's true. Even outside of the group that had negative concentrations and apparently no water in their bowls at some point, that's fine. Things happen in experiments that may go wrong, or the data gets confused or whatever it is, but you need to be aware of that and not tell me that they're precise and accurate, because they're obviously not. And another thing is good to actually go see what the current state of the literature is, right? So looking to see what the actual solubilities of some of those compounds are, looking at actual solubility charts. And I know you guys don't know a lot about those things, and so it's very difficult to get up to speed on those. But at the same time, you want to know how well your data compares to other data. So anyway, kind of enough about the lab report. Y'all look over those. We'll come back to those. I'm going to improve my rubric. We're going to get moving on those, and do expect those to be graded a little bit more rigorously next time. So don't sort of, hey, I got an A on that. Great, I'm good to go. You are not good to go. You are good to go for that one, which is why you have an A on it. And we'll expect an improvement from y'all, just like y'all expect improvement from me throughout the year. So we'll be talking about this another day. All right, great. So now, on to our chapter. Okay, we're going to cover 4.1 and 4.2 today. You may think you are already familiar with the periodic table because of the work we've done with it so far, and you guys are sort of have a cursory familiarity with it. By the end of this chapter, you're going to be real familiar with it. So as we've pointed out, I think some of you guys, we kind of laughed about it. Whoever thought that any of these guys would be helpful for people, I'm not sure. This is Mendeleev's original sort of table, and this was, of course, the first stab at it. And I have no idea who any of these came from, but they clearly are not the most useful way to organize it. All right, so just real fast, let's get in our heads what our objectives are. Let me make sure we're in focus here. Okay, that's probably the best we're going to get. All right, So describe the general structure and arrangement of the periodic table of elements. Okay, I think we can probably do that one pretty well already, but we're going to go back over that just to make sure everybody's clear about it. We want to identify the names and locations of the major regions in the periodic table, and because of the way it's organized, we can even have regions, which is part of the helpfulness of it. Identify names and locations of the elements in groups 1, 2, 3 through 12, 16, 17, and 18. Also identify the groups known as rare earth elements and the names of the 2 rows of these elements. Okay. State the 2 collective names for groups 1 and 2 and 13 through 18. And state the chief chemical property that distinguishes the metals from the non-metals. All right, so nothing like super crazy, nothing super pulse pounding here, but it is sort of the basic stuff that's going to really let us get into the stuff that's really interesting. And by the way, I will be sharing the link to the interactive periodic table of the elements, which is a super website, and it lets you click on a bunch of different things, lets you see the orbital diagrams, lets you see the what phase they're in, liquid, gas, or solid. At any, you have a temperature slider, you can move back and forth, and it'll color them as different things to see when everything is sort of a gas, when are most things solid, how hot do they have to be before most things on the chart are liquid. It's pretty interesting. So you can do pretty much everything with that, and I'll be sending you guys that link for your use throughout the I guess the semester, the year, whatever. I use it all the time when I'm tutoring folks, and use it even when I'm preparing to talk to you guys. All right, sorry about that. Okay, so as we're talking right here, you guys probably want to have your book sort of turned like that, so you can be looking down at it. And I'm just going to kind of do this because I'm looking more at the words than at that, although I may move it around a little bit here. So just, take note of here, kind of, you see what I've got highlighted and underlined. Just this guy's name, Dmitry Mendeleev. And I'm sure he said it much cooler than that. But so he's way back in 1869, which, again, you guys just got done doing your experiments and found out very quickly how badly things can go when you're not being super careful. And you guys have electronic balances, and you have easily controlled heat sources. These guys didn't really have a lot of that. You can imagine back in 1870, they're still shooting musket balls. They don't have any kind of factory production for things. Very difficult to get accurate weights. I mean, it's just like everything that's hard about lab technique to the 50th power is that much harder. But he had already arranged 67 elements into a table. And he did that based on some of their properties, okay? And he even was able to predict the existence of several unknown elements based on gaps as he had organized it, okay? And so that's one of the things that we know when a theory is really robust and really it's not about being useful, really, but that's kind of it. When a theory is doing what a theory is supposed to do, it can make predictions, okay? And so if he's putting together a table and saying, hey, guys, I think there's an element that's missing here, and then 20 years later, somebody finds an element that actually plugs in and fits right there, that's a pretty good sign that that is a robust, true theory, or at least is on the right track. Obviously, he had some things missing, as we'll go into for your homework before next class. But it was a huge step forward towards understanding how the world was organized. Also, let me just point you guys out right here. Periodicity. Okay, what does it say it is? A regular cyclic variation of some kind. Okay, so if we see that something's happening every 3 times or every 5 times or something like that, you might say, hey, there's a pattern here that means something. It's meaningful. And so that's what these guys were doing. And you got to remember, like, we've talked about this a little bit, how so much of chemistry is sort of like groping in the dark, trying to figure out where you are with one hand tied behind your back. Everything's super tiny. Everything is, you don't know whether water is an element or a compound, because you can't seem to break it down no matter how hot it gets or how cold it gets or how much you smush it or how much you mix it with other things. It always seems to come back to being water. And so for a long time, it's really hard. How do you know? What's the process? And it really wasn't even until electricity was used to break it down in electrolysis, which we'll talk about later in the year, what that is, that they even were like totally confirmed into what water was. So again, I know you guys have prepared for class and read this and highlighted your own words and pages here, but I'll just point it out just in case we didn't all highlight the same thing. Just note some of this. And I think it'll be helpful for me to go through it and for you guys to actually go back and read through like what exactly was going on. But if you look at tellurium, and again, just swap your book around there so you can see it. Z equals 52, and remember Z is our atomic number, and iodine 53. Okay, look at their masses. They don't go up the same way that most of the other ones do. So as you kind of look along those masses there, they go up nice and cleanly, except when you get to, all right, I'll flip this around right here for you. Tellurium and iodine, you can see those masses right, they're in the wrong order. Tellurium's the lower number, and iodine's the higher number, atomic number wise, but their masses are not in that order. And that's because tellurium has got an extra neutron in there, and that throws off the mass calculation there. But so what they're doing is they decided they needed to organize them according to proton count, which we'll get a little bit more into as well. But what really sealed the deal is right here. But iodine exhibits all the properties of the group 17 elements. And so that was strong enough for him. He said, I don't know what's going on. I don't know why the mass doesn't work out, but it acts like all those other guys, bromine, chlorine, fluorine. It acts like them, and it needs to be in that column. Okay, and so again, a theory can be, again, like the word I keep using is robust because that's such a good word for a science theory. A theory cannot explain everything and still be a good theory. As long as it's sort of recognizing, hey, I don't know why this is, but I know that all of these other things match up. So unless somebody can explain more things than what I've got, then they need to go along with my theory. Astronomy is often that way too. Everything's kind of indirect and sort of, you're inferring and using long chains of deduction to figure things out. And you basically say, all right, I think this is how neutron stars operate. Somebody needs to prove me wrong if we're going to go in a different direction. So anyway, so you can read on there. Noble gases were not known in Mendeleev's time, and he provided no place for them in his table. And of course, when they were discovered, he was resistant to accept them. That's always the way it is with these really famous scientists. They're like, I got it all figured out, and anybody who's bringing something to me, they're really resistant to it. So in theory, they should just accept it because they're good scientists, but in reality, there's always pride and professional challenging and all of that stuff going on. So anyway, eventually, you can see right there, it says noble gases are added as group 18. Okay, and we'll get a little bit more into this here. Note that 99 through 118, flip the page over up here. Sorry, I'm off the thing there. There you go. Been synthesized in the laboratory. They do that in big particle accelerators. It takes a lot of energy, and they all have very short half-lives, which is something we'll talk about later. But basically, half-life is how fast something breaks down into other elements. And a lot of these have millionths of a second of half-lives. And so without reading up on it, I don't even know how they are able to detect those. I don't know exactly what the methods are, but it's not normal stuff like you find it, dig it up, and oh look, hey, this is element 117, because 117 becomes something else radioactive, and which breaks down itself to something else radioactive very, very quickly before you could even look at it or note its mass or anything like that. So, all right, nuts and bolts here. Columns in the periodic table are called groups, and rows are called periods. Guess what? That's going to be on a quiz and a test. All right, just basic nomenclature. Again, we're learning the language of science. We're trying to make sure that we are fluent in that language. So I'm going to require you guys to know those things. Okay, so they're called groups, and the rows are called periods. And figures 4.3 and 4.4 give you different group areas of it. Okay, so on one level, the first level, the most, I guess, fundamental level, we've got three different groups. We got the metals and we got the non-metals. And in between are things that are sort of metallish, so we'll call them metalloids. All right, that's literally, you can just see that they're the ones that are in the borderland there. It means they've got some properties of metals and some of non-metals. All right, and again, we're right here. What's different about this? Well, this is just that group that's from down here slid up into the thing to show you kind of the whole deal here, all in once, even though that's kind of awkward to use, and we don't do a lot with those, so it's a lot easier to shrink it down to this one here. All right, and so a lot of things that we commonly identify as metals obviously are in this group, but we want to not just think of metals as only those things that are common to us. Of course, we just kind of look through what are some metals that are super common: iron, nickel, zinc, copper, silver, gold, mercury. All right, those are all metals. We tend not to think of sodium as a metal, or rubidium. We probably don't think about it at all, to be honest. Or all these uranium, we don't think of that as a metal. Okay, but it has these properties that all metals share. All right, so what do they have? Common physical properties: high electrical and thermal conductivity. So heat moves through them very easily, which is why when you touch a hot pot, you know it very, very quickly, whereas if you touch a hot car seat, they might be the same temperature, but boy, is that metal pot going to conduct heat into you a lot faster and burn the fire out of you. All right, electrical conductivity, best conductor in the world is gold, followed by, I believe, silver, and then copper. Well, guess what we use? We use copper because copper is way cheaper and it doesn't lose too much of the conductivity. But that means these electrons float very easily through it, which means electricity goes through it, which means we can use it to transfer power. Malleability, able to be bent into different shapes with, able to be moved without breaking. Ductility is a similar thing. I believe ductility is able to be drawn into wires, which is a specific form, and we'll talk more about all these cool things that they can do as we get into maybe some interesting little projects or reports or whatever. But there are tests for all of those things. Steel has a thousand different types of steel with different things like cobalt and nickel and titanium, different alloys that are in there. A mixture of a metal is called, different metals are called alloys. And they've all got different properties. Some are more ductile than others. Some are more malleable than others. And so anyway, so you could go on and on with that. Luster is how shiny it is. So maybe, you need to be able to name 2 or 3 of those that metals have, just as you're thinking about things to record for your quiz / tests on this chapter. All right. Need to know that losing an electron to form positive ions. Okay, so we talked about ionization. Metals are easy to ionize. Okay, that means easy for those electrons to leave. Okay, and of course they're negative. So when you lose electrons, that becomes a positive ion, and that's known as a cation. Okay, one of the fundamental things you need to learn and take away from this year, not just this chapter, this year, the difference between cations and anions. Just go ahead and memorize it. Okay, whatever mnemonic you need to do to memorize that, you need to know that cations are positive ions, anions are negative ions. Okay, we will talk about ionic compounds later. All right. So moving across here into the metalloids, just these 1, 2, 3, 4, 5, 6, 7. Not clearly metallic, not clearly non-metallic. Okay. In some conditions, they conduct electricity. In others, they don't, which is why they're called semiconductors, part conductors. Okay. Which, thankfully, we have these because silicon is what all computer, well, technically they're called logic gates. We call them circuits, or they have become microcircuits, and then now we have microchips with billions of those on them. They're one of these, silicon, germanium, astatine, I think is what that is. They have all slightly different properties, but in one situation where you've got the silicon in a particular arrangement, it conducts electricity, and then you hit it with a certain amount of voltage and it doesn't conduct electricity, and you can use that as a yes no 1-0 logic gate there, which is what all computing is based on. Okay, so those semiconductors are pretty useful for that. All right, and then nonmetals, typically they form negative ions by gaining electrons, so negative ions and ions. And they bond with each other, something metals almost never do. Okay? And I think this is just a typo here. They almost never don't do. Almost never do is what metals. So these bond with each other. Okay? So like CO2, okay, NO2. A lot of these all bond with one another, whereas carbon bonds with lots of things. But these guys don't do this. Now they bind together, so you melt a bunch of gold and a bunch of silver and you mix it all together, and you're not to form an alloy. You're not going to be able to pull them apart because they don't like each other, but they're just not chemically bonded to one another. They're physically bonded to one another. And on a very small level, but not quite the chemical level, the way like CO2 is bonded and made a chemical bond there. Okay, so just keep that in mind. Just note these things that non-metals bond with one another, whereas metals don't bond with one another either. And to finish us out here. All right, we're not going to be super fixated on this, but you are going to have to know some of them. Okay, and these names come from sort of the old days. They had all these weird names because of chemistry was sort of this new science, and people had known about. I think lime used to be called bituminous earth, and you're like, what? Why does that, or diatomaceous earth or something? It's just got these goofy names. You're like, earth? What is that? Why is it even called that? But anyway, so we're gonna memorize them. We're gonna move on, and they don't really mean a whole lot other than this is what they're called on this. So we got alkali metals, alkaline earth metals, Transition metals, pretty easy to remember because they're transitioning from one way to the other. Chalcogens, halogens, and noble gases. And I would say of all of these, and we got the lanthanide and actinides down here, but of all of these, I think these two are probably the ones that actually get used. Because people talk about halogens on a regular basis in various fields, engineering, chemists, physicists. They'll all talk about halogens because they're very active and they do all sorts of very damaging and dangerous things. They create free radicals. So anyway, that's a common name. And then, of course, the noble gases, we've talked about that, and we've used that regularly, although I don't think we've said any of these other names. So noble gases are the way to call those just in regular speech. And sometimes these are called inert gases, which you'll see in this Asimov piece as well. And as he said, I didn't know this. I learned this. This group 14 is the crystallogens and the pnictogens. I had never heard those. So anyway, just keep it in your mind here that we got the groups and the periods. Groups and periods. All right, so your homework shouldn't be super hard on this. So we'll get ready to move into 4.3 next time and get into some of the little more detailed trends in the periodic table that they have seen and have clarified some of the internal structure, let's call it, of the periodic table. So it's one thing to organize them by oxidation state and whether they like to form cations or anions, or whether they conduct electricity, or whether they're a certain silver versus more of a reddish gold, or those are all outer stuff that you can see even back in 1870 that let him do 67 of them. And knew there were some gaps, but he already had 67 of them. Now, today, we've done a lot more detailed work. And you can see atomic radius and things like that. But we'll get all into that next time. All right, so I was just checking the assignment sheet there, and I just remembered that I didn't actually give you any of these chapter exercises. They're pretty much just fact things that you're not really thinking a whole lot on those. And so what I'm going to do is I'm going to send you guys upload it to ClassReach this fantastic write-up by Isaac Asimov in a book that I got for 50 cents and is like 1,000 years old. It's not 1,000 years old. It was written in like 1960. But it's got some really good analysis of the periodic table, some of the history that I think really highlights some names that are going to be important later in the year too, and you might even notice some of them being a little bit familiar and like, hey, I didn't even know they did chemistry. So we're gonna really get into some of the noble gases and oxidation states. That is going to be a new concept for you. But he's got a really good way with words and is even sometimes a little bit funny, which is a relief in chemistry anyway. And so this will not only give you a little bit of background on the periodic table that I think is both edifying just because it's interesting, but also going to give you a little bit more of a foundation for learning some of the things we're going to learn, and how much work just went into discovering even the most basic stuff. I mean, look at this setup, man. Like, he had that custom built by somebody, and that prism was not something he just ordered from Amazon. So just a lot of work that went into it, and just really, I think, interesting and give you some background. So I'll send this, and I'll have questions that go with it. We'll get those questions answered, and then we will. You'll need to read section 4.3 for next time, and you need to read 4.3, I think, because there's a lot in it. Okay, so today's pretty light, pretty topical. We're pretty much just skimming the beginning surface here, and 4.3 is going to get real about a lot of this stuff that's going to be real useful for the coming chapters, and so we need to make sure we understand it. And I want you guys not to be afraid to tell me that you don't understand stuff or I'm leaving you behind. We're gonna slow it way down if we need to. I'm not gonna bore anybody, and it's not gonna just be easy because you guys don't want to put in the time. But if we're struggling not to just drown in a wash of chemical information here, we need to back it up a little bit and just make sure we're clear on the basics so that we don't get further and further behind. I know that's really worrying for some of your parents, and well, you don't have to tell them. I tell them, but just don't be afraid to tell me that you're drowning. Okay, and I'm going to throw you a life preserver. We'll get together. We'll whatever, sit down at cups and go through it until you understand it. Whatever we need to do to make it work. Okay, good deal. If you have any questions about your lab report, let me know. If you have any questions about the bell ringer, let me know. If you have any questions about the Asimov questions, let me know. Don't just send me homework that you don't understand, okay, which means you maybe need to look at it a little bit beforehand. All right, good. Well, if y'all have got any time left in your class, y'all can start working. Let's see, will you have these questions? Perhaps you won't have these questions. Well, Ms. Barron can use up the time. There are plenty of questions at the end of the chapter, should you guys want to go over them and discuss them to really reinforce some of this, but I don't know where you guys are in the class time, so I'm just going to stop talking and let Ms. Barron handle the rest of the time there. All right, well, I will see you guys on Thursday, and we'll talk then. Thank y'all.